Okay, why do we need actually, let's discuss direct digital manufacturing. What are the main motivations behind direct digital manufacturing approach? First of all, these days we prefer to have unique shapes. Everyone wants to have specific products according to their, let's say, properties and their needs. And another thing we need to have direct digital manufacturing is that the complexity of the parts are getting increased, and we need to have sometimes very small number of, let's say, products for a specific part. We need to produce in a shorter time, and that's why we want to have such an approach, direct digital manufacturing approach. And the advantage of digital manufacturing is that you can produce what you design. This is one of the main advantages. You don't have much restrictions on your design. And another thing, we can easily record the designs since they are digitally available. And another thing we can make use of direct digital manufacturing is that you can produce the spare parts at your home. For instance, your washing machine may be broken, some part of it may be broken, and you can easily obtain the digital file of it and then produce at your home or at an, let's say, facility which has such additive manufacturing machines. You don't need to have, obviously, specific tools to produce your part. Things are much simpler in additive manufacturing, and we want to make use of all these advantages in the direct digital manufacturing approach. So now let's briefly compare two companies. The first one is Rapid Prototyping Company, and the other one is Direct Digital Manufacturing Company. I would like to focus on what are the differences in terms of different properties. First of all, let's have a look at the certification equipment. In the Rapid Prototyping Manufacturing Company, it simply acquires the machine and then performs the manufacturing. The quality of the resulting product is not important, but in Direct Digital Manufacturing System Company, the quality is highly important. They need to calibrate their machines from time to time on their own. Let's have a look at the type of personnel they have. In the RP company, Rapid Prototyping, we don't need to have highly experienced. Any formal testing is required for personnel, but in the Direct Digital Manufacturing Company, the personnel engineers should have experience in additive manufacturing. They need to be certified. In the Rapid Prototyping companies, they can follow a trial and error approach. They can produce a simple part. If it's not functioning, not proper, they can throw it away and produce another one. But in the DDM, in direct digital manufacturing, the tests are highly important. The resulting product might be a bit costly, so they need to consider each step and have such certifications for all their sub-steps. And in the RP company, we don't need to have high quality. You can simply have manual inspection, visual inspection, but in the direct digital manufacturing companies, we need to have ISO compliance in terms of quality, and they need to have an extensive quality system. And in terms of manufacturing systems, RP companies have very simple systems, basic systems, and they don't need to have high documentation. But in the DDMs, we need a proper system for storing the files, checking all these documents. So they should obey again to some different quality, let's say, requirements. In terms of planning, again, RP companies are much simpler, but in the direct digital companies, they need to have formal, much professional process plans, process chains, while they are producing such products. In terms of scheduling and delivery, they don't have any obviously professional delivery systems or scheduling systems in the RP companies, but it's much more sophisticated in direct digital systems. They need to respond to this customer's need, and as in shorter time possible. They can have just-in-time deliveries. For instance, they may be working with an automobile industry, and the automobile industry may give them such that weekly plans or monthly plans, and they need to obey these plans and provide these spare parts or other parts to these factories in time. And we discussed about the personal. I don't want to go through it once again. I mean, the vertical integration, if it happens, it's useful, but for the direct digital manufacturing companies, we need to have such vertical integration. We need to have some levels, and there need to be information flow between these levels. So in summary, we can say that DDM companies are producing the parts in a more expensive way, but their qualities are much better, and their also costs are higher than the conventional processes. For instance, considering stereotypography and SLS systems, the cost of a part might be around $5,000, since they have other extra costs, machine costs, engineering costs. So the cost of even a simple part might be around $5,000. And if the part is smaller, obviously, you can decrease the fabrication time and the cost, since in a batch, in a build table, you can produce many of them at the same time, and this will decrease your overall manufacturing and overall cost of your products. So let's discuss cost model of any manufacturing process, any additive manufacturing process. But before, do you have questions regarding these issues? Why are we actually doing direct digital manufacturing? What are the advantages of such enterprises compared to rapid prototyping facilities? No question? Okay, now let's have a look at a cost model. A cost model of an additive manufacturing machine. And in this cost, we will have some sub-items. What are these? We need to have a machine cost, since you are investing some money. So we need to include machine purchasing cost. And then we are operating this machine after you purchase it. That's why we need to have some operation costs. And we are using material cost, labor cost. So these are the main items which are actually adding up, and we obtain finally the overall cost of our product. And this is the cost for some number of products, and this is the cost for a single product. We can say that it's the cost per product. So it's equal to this equation. We have purchasing cost, operation cost, material cost, and labor cost. And later, if you divide it to the number of products you have, you can obtain cost per product. So this is the first type, first category, first item, purchasing cost. So we have a price, the cost of the machine. For instance, this might be, let's say, $1,000. And then we have some parameters, as you see underneath. We are dividing this value to the below items, so that we obtain a purchase cost for a specific product. We cannot have this $100,000 into this, impose it into a single product, since we will be using this machine for some number of years. And this is here. This is a useful life of the machine. It should be given in years. And then we have another parameter, 0.95. This is the uptime of your machine. We are assuming that your purchase machine is actually producing products about 95% of the time during this year. And this is not a fixed value, obviously. If you are not using it 95% of the time, then you may, for instance, set it to 0.65. It's just up to your orders. You can decide on it and try to come up with an purchase cost. And TB is actually time for building parts in hours. So if you need to multiply it with the price and then divide it with the years, the number of years you're going to use this machine, days and hours, and lastly we have a factor here. Since this part is in hours, you need to also have the TB, the time for build, in hours. So if you do this multiplications and divisions, you can obtain the purchase cost of a specific type of product. Any questions, guys, about the first item in our cost model? Okay. Now let's have a look at the second item. This is operation cost. What do we have in it? We have only TB times C0. So TB was build time, if you remember. This is TB build time of our product in hours. And we will be using it also in the second item of our cost model. This is it. We obtain the operating cost with multiplying also the time with cost rate of the machine. And it's obviously a function of some properties, the machine maintenance cost, the utility cost, for instance, energy, the electricity. You need to have a cost for the factory space, and also you may have some other overheads, for instance, transferring of your part or transferring of the raw material. These may be all included in this specific cost rate of the machine. Then we have the material cost. It's much more complicated than the previous one. It has many factors, many constants sometimes. We have KR as the additional material consumption. Since if you are using, let's say, powder bed or SLA, you have, for most of the time, an extra material which is not actually used for the fabrication of the product, but they're available in the tank or in the bed. And we cannot always recycle this material, and that's why you need to include it in this material cost. And sometimes we are using support structure, and that's why we need to also include in the material cost. And we have the basic thing here, cost of the material per unit mass. This is CM, and that's why we need to multiply with mass. So we obtain the mass by the density and the volume of this material. Question, Murat? Okay. And then we have the labor cost. It's a very simple one. We multiply with T1 and C1. What are these? I think we have it. But I think not included here, but not complicated. You can obtain the labor cost by simply multiplying T1 and C1. These are related to the time your workers are spending in your factory and their cost. So if you sum all these items, then you can obtain the overall cost of a specific product, and then you may add your, let's say, other things and give the customer the final cost of their product. Now let's briefly have a look at the build time model. Since in these additive manufacturing systems approaches, cost and the time are the most important things. We have gone through the cost model. Now let's have a look at the build time model. And in the cost equations, we have this parameter, the build time of the product, TB. Now we'll discuss the details of it, how we determine TB. Some CAM software is providing this TB to you. You don't need to actually do any calculation on your own, but in some cases you may need to do it yourself and try to come up with an estimate of build times. So what affects actually the build time? The size of your part, the shape of it, for instance, its length in z-axis, its orientation, the number of products actually you're going to produce in the same table, in the same bed, and also the speed of your machine directly affecting the build time. So we have 3 items in this build time: TS is the scanning time or deposition time, depending on the type of additive manufacturing technology you are using. Again, TR depends on some technology. For instance, we have coating in SLS, SLM, or in DLP sometimes, or in SLA. And we also need to include some delay time, and probably this delay time will be between the layers. We also have some starting delay and ending delays, but most delay actually comes from the operations between the consecutive layers. Once you find all these values, time values, then you can see the sum and obtain the final building time. Now we will have some assumptions. What are these assumptions? Assume that you have a kind of a part in 3D. Assume that this is a 3D product. So we have such connection between the upper and bottom part. So we need to have a building box. This is called as building box, and it has X, Y, and Z values. Obviously, it's like, let me use a different color and try to show you the building box. Actually, that will be the building box we need to have to produce such a shape. And our part should exactly fit into this building box. We are trying to make it simpler, otherwise it will be quite impossible to do computations on the size of this complicated product. So we make use of the bounding box and things will be much simpler. We will only left with 3 parameters. The size of the bounding box in X, Y, and Z axis. Any questions, guys, up to now? Are you there? Are you following me?
Is the lines tangent to the object?
Yes, it needs the bounding box actually should touch this product from at least a point. In some cases, what was TR? I forgot it. Let me go back to it. Yes, TR is coating time. I mentioned it. It might be 0 depending on the case. But the support structures, again, in some cases, it may be 0, but depending on the technology you are using, you may need to have some support structures. For the calculation of the time, we have some parameters, the number of layers we need to have for the production of these support structures. And this TRS is actually the time we need to spend for coating of support structures, coating of the layer of support structures. And then we have the other term, which is LP times TRP. LP is the number of layers which is required to produce the given part. So we can obtain it by checking the building box, the size of the building box in Z. And if you divide it with the layer thickness, this is layer thickness. And if you have this division, you can obtain the number of layers. And once you've got it, then you can multiply with the time you need to spend for coating for each layer. You can obtain this part. And if you multiply number of layers, since in some additive manufacturing processes, you don't need to deal with the support structures at each layer. You may work on the support structures maybe after 4 layers. So if that's the case, you may have different values. But if you are dealing with the support structure at each layer, then you don't need to have a specific LS value. It might be equal to LP. So it's a general equation. That's why we are assuming that the number of layers for the supports might be different, and for the other part, build part, it might be different. Another case is that, for instance, you may have such a shape, and you may not be producing support structures for the whole layers. You may be producing for just, let's say, 100 of the layers, but the part might be composed of 400 layers. So that's why you need to have such an equation for calculating the time you are spending for the construction of support structures. Any questions, guys?
Hocam post proses falan olduğunda bu hangi part'a giriyor ya da build time'dan değerlendiriliyor mu?
No, it's not included in this build time, since it's spent after the part is manufactured in this additive manufacturing machinery. It's something different. You need to calculate it with different equations. And if you remember, in real time, we also have a parameter called scanning or deposition time, depending on the technology. It may be a scanning, for instance, if it's an SLA, we are scanning the layer. But if it's a direct deposition technology, we are depositing material, so it will be in deposition time. And while calculating this TS value, we need to be aware of the cross-section area for each layer, since, for instance, in SLA, we were covering, if this is a slice, we were covering the interior of this cross-section. So the area of the cross-section is important. It will directly affect the TS value. And obviously, the scanning type, the scanning filling technique strategy is affecting our overall scanning time. Since if it's a point-wise, then you will spend more time. If it's a line-wise, then with a single pass, you can determine it. If it's a layer-based, then maybe just few seconds will be enough to cover this whole slice. And also the deposition or scanning time, the number of layers is again important. We can multiply the time you are spending for a single layer with this value and obtain the total amount of time you are spending for deposition, or let's say scanning. Here you see the example. For instance, we have an SLA system, SLA 7000, one of the earlier versions. We have 18 parts laid out on this plate. And how many products we can produce, we can obtain by simply, this part is responsible for the number of parts we have on the x-axis. This is for the number of parts we have on the y-axis. So this is our whole size, and we are dividing it with the bounding box of our shape and some extra safety values. Assume that this is, let's say, 10. The size of your building box is 10. Then you may have 2 millimeters of gap between each part. So that will be 12, let's say. And the upper side is actually corresponding to the size of your bed and some other safety values. So this is our size of our bed in X. Again, we have some safety issues. So if you come up, let's say 124 here, and it was 12 in the denominator, so we can say that you may have 10 number of products in the x-axis, and you can do the same for the y. If say, let's say if it's 5, then if you multiply these two, you can have 50 number of products in this build table. Any questions about this computation, simple computation? So the most important, actually the difficult part is to determine the scanning time. And the scanning time obviously varies between the products you have, varies between the cross-section area. It depends also on the laser diameter. It depends on the distance between the scans. And for instance, this is your, let's say, diameter. And we have some gap between this hatches. And also it depends on the scanning speed, average scanning speed. So it's quite complicated. You need to be aware of all these parameters and then finally determine the scanning time. To make it actually simpler, we will have a parameter about an average cross-sectional area, and it will change with respect to the part. But for a specific part, we will, let's say, all the slices have an average cross-section area of, let's say, 75 millimeter square, for instance. And this will not change between the layers. That will be an approximate value, and we will be using it in our build time estimation. And you may obtain this actually average cross-section area by multiplying your bounding box in the size of your bounding box in X and Y, and then this factor, this correction factor. So it will give you an average cross-section area. And then after you got this one, this average value, you can determine the scanning length. But how? Any idea do you have how we can determine the scanning length? Assume that this is our again cross-section, and I now calculated the average area. I know that this average area is, let's say, equal to 75 millimeters square. So how can I determine the length of this scanning? And if I'm going to cover the area in 100%, so it should be covered totally, what will be the length of the scanning? We have an answer on chat. Any idea? Any other answers? Or is your friend is proposing an correct answer? Any idea? Any other than Hüseyin Furkan?
Aralığı bilmemiz gerekmiyor mu hocam?
Sorry?
İki hatch arasındaki boşluğu bilmemiz gerekmiyor mu?
But I say that it's filled completely. So if it's filled completely, then the equation your friend is proposing is okay. You can simply divide this value with the laser diameter, and you can obtain the length of your laser. Obviously, it will not be correct 100%, but it will be quite fine. You can use it in your other calculations. But if you're not filling the interior completely, then it might be a bit complicated. You need to also consider hatch spacing, and things will be more difficult. Any questions, guys? So we have some assumptions. We are assuming that hatch spacing is kind of a percentage of our laser beam diameter. Another assumption on the support structure. So the support structure needed is a kind of an actually depending on the cross-section area. And we are assuming that it's about 30%, and we have support structure kind of fraction. And in the no support cases, we will take this percentage as equal to 0, and we need to have a layer value. This is the number of times a layer should be scanned to fabricate the layer. For most of the time it's 1, but depending on the type of material you are using, it may be 2, 3, or 4. This NST value. Then once you determine all these values, you can determine the time you need to have for scanning. As you see, we have average cross-section, we have number of scannings, and we have hatch spacing, we have laser diameter, we have parameters for support structures. And once you know all these parameters, you can determine the time you need to spend for scanning. This is how we do it and obtain. We need to consider obviously the scanning speed. It's in hours, and you need to convert into seconds. Any questions, guys? Okay, this is the last parameter, delay time. So in this delay time, we need to consider the platform moving time in z-axis, and specifically we can also have coating delays, and also in some applications, in some machines, we need to have post recoating delay. And if you remember, some machines have nozzle cleaning systems. So after, let's say, some number of layers, your head needs to go to the cleaning stage, do the cleaning, and then come back to the fabrication. And in more complicated systems, from time to time, the sensors might be calibrated, and you may need to wait for, let's say, the extruders reach the temperature value. So you need to include all these in your delay time item and have the final delay time value. So this is not that complicated. And once you all have these time items, you can finally obtain the real time value for your manufacturing application.